Hello and good evening, and welcome to week 8 of the tutorial session for problem solving on WBG device-based power converters course. So, just a second, is my voice audible? Hello, is my voice audible? Hello, is my voice audible? Hello, hello, is my voice audible? Hello, hello, is my voice audible?
Yes.
Okay, I'll just try to be a little louder, but yeah. Just share my screen then. Okay, I hope my screen is visible. So, so till the last class, we were seeing actually a particular problem on switching loss computation, right? So as part of that problem, we had seen how to compute the current rise time, voltage fall time, turn on delay time, right? And correspondingly the di by dt and then dv by dt. Correct? So after we computed all of that, we kind of jumped into how we compute the switching losses, right? So that is something we saw. So moving on from that, right? So last week it was, till last week it was about switching behavior and switching characterization. Okay. So Yeah, so we just saw the mechanism of how the turn on and turn off happens within a device, right? And then using KVL or first principles, using KCL and first principles for an inductor and capacitor, we kind of derived how to find out the turn on delay time, rise time, and then the voltage fall time. Okay, using the gate current, right? We kind of assume that the even though it's first order RC charging circuit, we kind of linearized it, right? And then we computed the uh, corresponding times. Okay, towards the end, we saw that once we know what is the time, what is the switching time, right? We saw how to compute the energy, right? So you have your current waveform over here, voltage waveform over here. You kind of compute what is the instantaneous power loss, and then you kind of find out the area under the curve, right? So area under a power curve gives you the energy, right? And we saw that this energy loss happens every time the device turns on and turns off. So when you multiply that with the switching frequency, you get the average out power. Okay. So that is something we saw, and we have derived the entire thing for turn on. This is during the turn on transition. We also saw that something analogous to this will happen during turn off. We compute what is the turn off energy loss, right? And then we kind of compute what is the total power loss. So this is just your switching loss. Okay. That is the loss incurred just for the device to turn on and turn off. Apart from that, there will of course be the conduction loss of the device, which will be I square R, where I is your RMS current through the device. Okay. So this is how you compute the power loss. So today, in extension to this, right, we will try to understand once you know the losses in a device, okay, once you know the losses in a device, you know that the device is going to get heated up, okay. The device will kind of get heated up, and what would happen as a consequence is that the junction temperature of the device would increase. Okay. So if you do not have adequate heat dissipation mechanisms, right, what's going to happen is the device is going to, the device junction temperature is just going to keep on increasing. It will never settle to a steady state value. And what might happen is it might exceed the ratings given for the device. Okay. So for each device, if you go into the data sheet, you will see that the device is probably rated for between minus 50 to plus 150 degrees Celsius, or minus 25 to 175 degrees. Okay, that is the maximum operable temperature of the device. If your junction temperature exceeds beyond this, right, your device is going to blow up, and that is something we don't want. So today we will focus on solving problems that will give me what is the power loss,
Sir,
and based
voice
on
echo
that,
is there.
sorry,
Hello. Sir,
yeah,
your voice echo.
my voice is echoing.
Hello.
Yeah,
Yes, sir.
my voice is echoing. So are
Yes,
all
sir. Twice
others
hearing.
okay? So others, you are also facing the same problem. Selva Kumar sir and Anandi. Is my voice echoing?
No, sir, it's clear now.
So far, whatever I was telling, it was all echo.
No. It's clear.
Okay. Selva Kumar, probably you can leave once and then join, please. Okay. So today we will kind of see once you know what are the losses that are going to happen in the device, right? How will you calculate what is the junction temperature increase, and then as a consequence, how will you design the heat sink? Okay, this is a very essential consideration, and many a time what happens is because of insufficient design or because you don't estimate the losses properly, right? The device temperature would shoot up, eventually resulting in the device getting blown up. Okay, so today we will see about heatsink design. Okay, So I think part of heatsink design was covered in the lecture slides also. But anyway, we will, as we go through the problems, I think it would be clearer, right? Okay. So let me go back to the slides and let's take a new slide. Yeah. Okay. So I'll just note down a problem, and based on that, we will just try to compute. Okay. So let's take an IGBT. All right. So for an IGBT, the VI curve is given. Okay. So let me take a moment to properly draw the VI curve. This is going to be IC, which is a collector current, and this would be VCE. Okay. And then multiple curves are given over here. So you would know that for an IGBT, there is an initial on-state drop, right? On-state voltage drop is there. Unlike a MOSFET, for a MOSFET, it is only an RDS on which is there. But for IGBT, there will be an initial VCE drop. We call that at VCE naught. Okay, and then there will be multiple curves. Okay, so depending on the temperature, it can be something like this, right? Something can be like this, and so on. Okay, but primarily the dark green is the curve that's given. Okay. Okay. And what's given is this is 0.9. Okay, and you have this in volts and this is in amperes. This is 0.9. Okay, and then this is 300 amperes, and this is 3 volts. Okay. Okay. Now what they have given is In the problem, right, the IGBT is operated at an on-state current of 150 amperes. Okay, and let's say it's operating in a buck converter or somewhere, right, in a switching converter where at an on-state of 150 amperes with a duty D equal to 0.5. That is, you are operating the converter at 50% duty ratio. Okay, so find the conduction loss. This is a pretty simple one, right? Find the conduction loss. Find the conduction loss. Okay. Fine. So, did you understand this question? And by the way, let me write the part number in case you want to refer to this later. This is SKM 200 GB 12V. Okay. This is the IGBT. Okay. Part number. If you want, you can go and refer to this later. Okay. Fine. So this is given for you. And let's say that this is operating in a buck converter, right? It is operated at a non-state current of 150 amperes. That is, the device current is 150 amperes with a duty of 0.5. Okay. Duty of 0.5. And the question is to find out the conduction loss. Okay. Fine. So how will you find out the conduction loss? So what should be the first step for proceeding? Let's find. Okay, so one thing is, if you take a MOSFET, right? If you take a MOSFET, so let me take a new slide, okay? Yeah, so if you take a MOSFET, we earlier saw that it can operate in three regions, right? One is your saturation region, one is your cutoff region, and one is your ohmic region. So when the MOSFET is fully turned on, when the MOSFET is completely turned on, you know that it operates like a resistance, and this is your RDS on. Okay, so directly you assume that the entire device current is going to flow through this particular resistance, right? So there will be a drop, which you will call this as VDS, and there is a current which is IDS directly. Okay, so this is in case of a MOSFET. But can you tell how do you kind of approximate an IGBT in its on state, right? So yeah, and generally the diode is not intrinsic, but people add it externally. Okay, so this is your collector, emitter, and then gate. So how do you approximate an IGBT in completely on state, right? So that is how we should find out the conduction loss. This is the first principle. First, we should know how the IGBT behaves when it is completely turned on. Only then you can find out the conduction loss, right? So how does the IGBT behave? Can you tell? Will it be a pure resistance or is there some other part to it? So let's go back to the VA curve. So seeing this VA curve, can you tell how the IGBT would behave? In on state? Is my question clear? So if you take the VA characteristics of an IGBT, right? So if you take the VA characteristic, you will obviously see again there will be three regions, right? So one is going to be your insignificant cutoff region. Okay. So one is going to be kind of your cutoff region. Okay. And then what you would see is you will see something like this, right? And then you will see something like this. It's very similar to MOSFET, but there is a very small difference, and so on. So as VGS increases, right? So VGS4, VGS3, VGS2, VGS1, and this is for VGS less than V threshold. So this is your IC and this is your VCE. So can you tell, seeing this figure, so um, can you tell me what are the different regions of operation for IGBT?
Cutoff, linear, and saturation.
Correct. So cutoff, linear, and saturation. So cutoff is quite clear, right? So that is your cutoff region is going to be this particular region, right? It's quite clear. Okay. So what will be the linear and what will be the saturation? It's kind of opposite to MOSFET, right? I think you can recall that kind of these linear curves, right? All these, I mean, I should not call them linear curves. So all of these curves, or let's call that ohmic curve, right? All of these ohmic curves represent your saturation region in an IGBT. Okay. And after it approaches the knee point, right? After the knee point, so these regions are your linear regions. So in your IGBT, this is your linear region, right? And this is your saturation region, okay? And this is your cutoff region, okay? Now, if you compare that with a MOSFET, right? So let me just asymptotically draw the curves for a MOSFET, okay? So for a MOSFET, you may recall that you have something like this, which is VDS, this is IDS, but more importantly, what you will be seeing is this, of course, cutoff. Um, right? So there's something like this, okay? Okay, so compare this and this. What is the difference you are seeing? So there is an ohmic region in both, right? There is an ohmic region in both. That is fine. But apart from this, are you seeing any other difference? Any other difference between these two? Look at the x-axis, right? If you look
That
at the x-axis,
cutoff, no, the threshold voltage is certain point. It is from 0 to, there is some potential. Up to that, there is
correct,
uh,
correct.
not on.
So do you know why this comes into play? Over here, there is nothing, right? And over here, there is some cut-in voltage. We call this as cut-in voltage. Let's
13
call
voltage.
this as VCE naught. Okay, we call this as VCE naught. Do you know why this comes into play? So what is the why are we getting this? What is the property of an IGBT that makes it have this kind of a region?
It is
Which is
PNP, no? Is
correct. So it's basically a minority carrier device, right? So that is why it will have this small kind of a depletion region which needs to be overcome. You are right. Therefore, if you therefore deducing from this, we can see that for IGBT conduction, right, there are two barriers to be overcome. Not only the ohmic part, there is also this VCE naught part. Therefore, in the completely turned on region of an IGBT, we assume that, or we can model the IGBT as a voltage source followed by a resistance. Okay. if this is your C terminal, this is your E terminal, right? You have ICE flowing like this. This will be RCE, R collector to emitter, equivalent resistance. And, and then there will be a VCE naught. Okay, right? So from this you can understand that, okay, right? You get it, right? There is not just the resistance, but rather there will be this drop as well. So if you have to consider the power loss, there will be a loss due to this component, right? Loss due to this VCE naught and loss due to RCE. Okay. Okay. So yeah. Okay. So let me to the next page. Now that we have, now that you agree that the IGBT can kind of be modeled in the on state, that there is a resistance followed by IC. This is your emitter terminal and this is your collector terminal. This is your RCE. Okay. So can you tell me what will be the loss? So what will be PCE? P collector to emitter. IC is the collector. IC is the collector current. Okay. So what will be the loss?
VCE
IC
and
into RC.
into ICE.
VCE naught into IC. Okay. And then
Plus IC
plus
into RC.
IC square, IC
IC
square into
into RC. Sorry,
no, the loss will be IC square into RC.
but
Right?
last
Correct.
no.
Yeah. Loss is I square R, right? Drop will be ICRC. So the loss will be I square R, right?
Correct.
Okay. Now there is a very important part that we need to look. Okay. That is why I took the example of an IGBT and not a MOSFET. Now you tell me, you know that, let me take a current profile, something like this. Okay. Okay. I have a current profile, something like this. Let's say, for instance, so let's say this is I and this is T. So you know that this will be having two parts, right? The current has two parts. Okay. There is a net RMS quantity and there is a net average quantity. Okay. Correct. So you know that by definition, RMS and average, right? Average is quite simple. Average is just the area divided by time period, right? So this is your 0 and this is your T period. So you know that I average, or let me write this as capital I average. It is going to be 1 by T integral whatever is the time period 0 to T, I of T dt. Agreed? Is this fine? Correct? 1 by T integral 0 to T I of T dt. What about RMS? Can you tell me how RMS is going to look like? I RMS. Root means square. So from here itself you try to tell. So root is there. Okay. Let's get that out of the picture. So let us draw a huge root. Okay. Okay. So root means square. So root is there. And then there is mean. Mean means average. 1 by T integral 0 to T I of T dt. And then there is a square part. So I square of T dt. Do you agree with this? Is this fine for both of you? This is the definition
Yes,
of
sir.
IRMS.
Yes, sir. Yes,
Correct?
yes.
Okay. So now you tell me this current and this current, right? VC naught into IC and IC square RCE. What should be this IC? Should it be RMS or should it be average? Or we see we are calculating average power. Okay, I mean average power isn't like the power in absolute number. I don't want power as a function of time. Okay, so you tell me whether I should take RMS or average, or where I should take RMS, where I should take average. Do you understand the question? Yeah. So this is fine. Do you understand the question? So where will you take RMS and where will you take average?
Yes.
This.
Before cutoff, that cutoff point is average. VC not.
Okay.
Yes.
And then this I square R will be RMS.
Yes.
Right. So why do you tell that this should be average and this should be RMS?
Because this cutting voltage, it will be looks like what is the what is mm, there will be potential period to start in the device. There is no time. I mean, it's not. It will not come average value.
No, so
Sorry.
let me take.
Sorry.
Let, tell me.
The no, there will be because period to on, there will be a potential, that breakdown potential that will be taken as an average potential at before T. That means it is a T0 before T0. That is VC naught. We call VC naught. So that's why I told average right.
I don't think. See,
Condition right
point.
or wrong.
See, I will tell you it's from the definition. Okay. So I think we studied this. What is the definition of root mean square? Why does a root mean square come into play? Okay, so let me tell that I have a waveform, something like this, a periodic square waveform. Okay, so what is the average? Average will be somewhat over here, correct? Average is something like this. Okay. So why does this definition of RMS come into play? Right? Why does the definition of RMS come into play? The definition of RMS comes into play because RMS gives the amount of current, right? RMS gives the amount of current which will give rise to the same temperature rise. Okay, so you would have studied this. Just a second, I have to change my device. I don't know why. Okay, so the definition of RMS comes into play because that's the equivalent current which will give rise to the same temperature rise. Okay, if a steady state current was passing through it. So that means that, see, let's say I have a current something like this as I have drawn. Okay, so let's say I have a current something like this, right? And then I pass it through a resistor. Okay, I will pass this kind of a current through a resistor. Now what will happen? There will be some I square R loss. Okay, and the resistor gets heated up. Okay, let's say that this is a heater only. Heater that we have in our homes. It's nothing but a resistor. Okay, you're just dissipating heat through the resistor. Now the point is, there will be some I square R loss, and because of that loss, the heater gets heated up. What is RMS? RMS means that is the equivalent amount of current. So over here, this is kind of a periodic current, right? On, off, and on, off, and so on. So what will be that value of current if I pass it like this, right? If I pass like this, the heater gets heated up to the same temperature. Do you understand? Like I am passing a periodic current, okay? The net effect results in the heater getting heated up. Okay. Now the question is, what will be that amount of steady state continuous current that will result in the heater getting heated up to the same temperature? Okay. Now if you have a sine wave, right? You have a sine wave, you pass it through a heater. Okay. The heater gets heated up. Why the heater gets heated up? Because there will be some I square R loss. Okay. Now the question is, you have passed the sine wave and the heater got heated up. There will be some I square R loss. Let's say the heater got heated up to a temperature T1. What will be that value of steady state continuous current, which if you pass, there will again be an I square R loss, and due to which the heater gets heated up to the same temperature T1. Okay. This current is known as the RMS of this current. Do you understand what I'm trying to tell?
Yes, sir. Yes, sir.
Okay, Anandi, is this fine? This is the basic of RMS. Okay, why did
Can you
RMS
explain it
come in?
again?
Huh. So let's say that you have a sine wave. Okay, you have a sine wave like this, and you pass it through any resistor. Any resistor. Okay. So what will happen after some time? The resistor gets heated up. Okay. Now you see that the average value of the sine wave is 0, right? Positive area is equal to negative area. Okay. But you are seeing that after you pass this kind of a current for some time to the heater is getting heated up, right? I mean, the resistor is getting heated up. So the average current is not responsible for the resistor getting heated up. There is something else in the sinusoidal current which makes the resistor to get heated up. Agreed?
Yes, sir.
Yeah. So now that particular value of current, right, or whatever is the quantity that is making the heater get heated up, right, even though the average value of sine is 0, that is called RMS. Okay. So it is like you are passing an AC current, the heater gets heated up. To, let's say the room temperature is 25, the resistor got heated up to 40 degrees. Okay. 15 degrees, there has been a temperature increase. Okay. The resistor got heated up to 40 degrees. Now, what will be that value of DC current? Okay, what will be that value of DC current? Constant current, which if I pass, the resistor will get heated up to again 40 degrees, same 40 degrees, right? Then it means that the effect is same, right? Like you pass a sine wave, the resistor got heated up to 40 degrees. What will be that equivalent value in DC terms, right? In what will be the equivalent steady state current, which if I pass through the resistor, it will again get heated up to 40 degrees. Do you understand this?
Yes, sir.
Right? Like நான் ஒரு current pass பண்றேன், ஒரு sinusoidal current. அதை pass பண்ணதுனால the resistor got heated up to 40 degrees, and then you kind of அது அது வந்து ஒரு sinusoidal current. இப்போ நான் ஒரு DC current கொடுக்குறேன். Okay, now எவ்வளோ value of DC current கொடுத்தானா resistor வந்து it will get heated up to the same 40 degrees. Okay, that is called RMS. Okay, so RMS kind of gives you in kind of a coded form, gives you that what I mean gives you the resistive effect or the heating effect in a resistor. Okay, that is why when you always calculate, you always make sure that this particular quantity is always RMS. I square R nale, I mean, if it is always I square R, it's going to be I RMS square R. Okay, and over here, as Selva Kumar sir was telling, this is going to be IC average. Okay, because why? Because this is the dissipative element, right? This is the dissipative part. It gets heated up. Okay, whereas this is like a lossy part. Okay, lossy part as in like you just compute what is the power due to this, right? The power will be V average into I average, right? So let's say you take a buck converter. Okay, you take a buck converter, you find out what if someone asks you what is the input power. Input power will be V in into I in, correct? V in average into I in average. Same way, this is something like VCE naught, which is a DC quantity, or a VCE naught is a DC quantity, right? It's a fixed quantity. VCE naught into I average. Okay, so do you understand this? How the power comes about? This is a very, very important question. I mean, this is generally asked in a lot of competitive exams, like you have your GATE or any other exam, right? This is generally asked. So if you have to compute what is the power loss is going to be I RMS square into R plus whatever is your voltage drop into I average. So you should know what is your I average and what is your I RMS. Over here in the question, they have given that ion is 150 amperes. You cannot just directly substitute 150 ampere over there. They have given that is why with a duty of D equal to 0.5. So with this, you have to compute what will be the I RMS and I average. Is this fine? How this power equation came about?
Yes, sir.
First, we have So first we understood how to model the device. That is, there is a voltage drop and then a resistor. And then if you know this, how will you find out the loss? I RMS square into R plus V into I. V into I average. Okay. Okay. Now the point is, let's come back. So let's say that this is a buck converter. Okay. So you have a buck converter. And this is where you are using the IGBT. There will be a diode over here. There will be the inductor, and then there will be resistor. I mean capacitor and then resistor. You have V naught, have V in. This is what we are talking about, and they have told that this particular current is going to be 150 amperes. Okay, 150 amperes, and D is 0.5. Okay, so just a second. Inductor is your current strip element, so this is 150 amperes. When the switch is on, the switch current will be 150 amperes. When the switch is off, the switch current will be 0. So how is your inductor current in the buck converter? How would your inductor current look like? Let's say this is IL, this is T. So your inductor current, they have given that duty is 0.5. So your inductor current would look something like this. Agreed? Is this fine?
Yes, sir.
Okay, this is your ripple. We call this as, some people call this as delta L, some people call this as 2 delta L, whatever is your nomenclature, you can follow, no worries. Now the point is they have not given any information about the ripple and all. Okay, so let's assume that the ripple is very, very small. So essentially there is only a steady state current, or inductor is as you know, a current stiff element. So there is a steady state equivalent current, right? Average inductor current is this. Okay, this is 150 amperes. Okay. Fine. So your IL was this. Okay. And then let's say this is your I switch or what this is your IGBT current. Okay. Your inductor current, as we told, it's going to be something like this. But I will assume that the inductor current is almost constant because they have not given any information. So I wouldn't worry too much about it. Okay. So I will assume that this is entirely something like this. Okay. Inductor current is entirely something like this. And this is 150 amperes. So what does the D period indicate in a buck converter? Or in any converter? What is your duty period? What do they mean by duty?
Duty.
It is the time for which device is on. Correct?
T on
So
by
it's
T.
like on
T.
huh? Correct.
T on by T.
Correct. It is a time for which your device is on. You're right. So this will be DTS and this will be TS. This is one switching cycle and so on. Right? So what will be your I switch then? I switch will be equal to the inductor current, right? I switch will be equal to the inductor current when the device is on, and it will be 0 when the device is off. Okay. Okay. Since we have not assumed any ripple, what I will do is I will just kind of erase this. Okay. And what I will write is, instead of complicating it, we will just have something like this. Okay. 0, 150 amperes, 0, 150 amperes, and so on. This is how your switch current looks like. Agreed? This is 150, this is 0. Okay, and so on. They have given that D is 0.5, so this DTS can be written as TS by 2, right? Okay, so in essence, what is your switch current? Your switch current is something like continuous square pulses, right? This is your switch current. Agreed? Do you agree with this? Is this fine?
Yes, sir.
Okay, fine. So now the point is we know what is the switch current now. We just have to find out what is the IRMS, what is the I average, so that we can plug it into the equation and then find out what is the loss. Okay, fine. So we saw in the earlier slide itself that your I average will be area by time period, right? Integration is basically area, right? Area by time. So this is basically area by time period. This is something like root over 1 by t integral 0 to t I square dt. You will just compute. Okay. So first, let's solve the simple case. What is your average? You look at this. So average will be something like this. What is your average? Can you directly tell? I switch average or IC average? 0, 150, 0, 150 with a duty of 50%. So what will be the correct? So it's going to be 150 by 2. Directly it will be 100 amperes. Correct. So this will be your I average. Right? Okay. So how do I find out I RMS? I RMS is right 1 by T integral. First we have to divide the so 1 by T integral 0 to T I square of T dt. Now if I divide I square of T piecewise, right? If I divide I of T piecewise, there are two pieces of I of T, that is constant 150 amperes for Ts by 2 period and constant 0 amperes for Ts by 2 period. So root over 1 by T, right? And then there are two intervals 0 to, let me take a new yeah. So 0, this is Ts by 2, this is Ts. Okay, and this is 150, this is 0, this is 150, this is 0, and so on. We saw this, right? So what will be the RMS? The RMS is going to be something like 1 by T integral 0 to T I of T square dt, right? So I will have root over later on, right? So 1 by T, I can split this piecewise. So 0 to T by 2, it's a constant 150 amperes when it is on 150 square dt plus T by 2 to T, it is constant 0 square dt power 1 by 2. Okay, so this is basically amounting to nothing. So what you would get is something like 1 by T into 150 square T by 2 minus 0, right? So basically your T and T are going to get cancelled. So 150 divided by root 2 amperes. Is this fine? This is how you will compute the RMS. Okay, 150 by root 2. Okay.
Yes, sir. Yes.
Okay. Now that we have computed this, we can just plug in into the power loss equation and then you find out what is the power loss. Okay. So the power loss is going to be, as we told, VC naught into IC average plus IC RMS square into RCE. Okay. So let's go back to the curve. Okay. So what is your VCE naught from this curve?
0.9.
Okay. So this is 0.9. How will you find out RCE from this curve?
This potential is 300 amps divided this 3 volt. Ohmic region 3 by
Correct.
300.
So this is yours. Correct. So RCE will be 1 by slope, right? RC will be 1 by slope, which will be 3 by 300, right? Or 0.01 ohms or 10 milliohms. Okay. So we'll just plug it in over here. So VCE naught is 0.9 into IC average was 75, right? 150 by 2. And IC RMS is 150 by root 2 square into RCE is 10 milliohms, which is 0.01. Okay. Um, so let's do the calculation. Plus yeah, I'm getting 180 watts. Okay, this is the power loss through the IGBT. Do you get this? Like how we did? Okay. Fine. Now the next part is once you have calculated what is the power loss, right? Mind you that this is only the conduction loss, and we have studied how to find out the switching loss in the previous class itself. We studied how to find out the switching loss. So in a similar manner, you will find out the switching loss, right? I'm not going through that right now. So let's assume that the switching loss is that only, right? So that day we saw a switching loss of 15 watts. Okay. I have seen switching losses 15 watts. So let's assume it is the same. Okay, I mean you cannot directly compare, of course. Um, let's assume that switching losses. For simplicity, let me take. Let's assume that the switching loss is somewhere around. Let's say total should be 50 watts. So let me take that the switching loss is 70 watts. Okay. In that case, your total loss, right? Total loss is going to be 180 plus 70, which is going to be 250 watts, right? So this is the first step in heatsink design. That is, you will compute the device loss. Okay, what is the loss through the device? All right. So we will compute what is the loss through that device, and then we will go ahead with the heatsink calculation, right? Okay. Just a second. I'll just open up the question. Now, if we go back to the, if we go to the data sheet, right? It's KM 200 GB12. Okay. It's KM 200 GB12. Yeah, semicron. They have not given the RT. Yeah. So if you go into the data sheet, I hope you can see over here, they have mentioned that the TJ, it can withstand is minus 40 to 175 degrees, right? And then all other details are given over here. VCE naught is also given around 0.9 we took. They have mentioned it as 0.94, which is fine. Okay. And RC is mentioned as about 4 milliohms. Maximum of 7.6. We have kind of overestimated it, but it's fine. Okay. See, we should be interested in this. R theta per IGBT is 0.14 Kelvin per watt. That means that for every watt of loss occurring, right, for every watt of loss that will occur, the temperature increases by 0.14 Kelvin. Okay. So for every watt of loss that occurs, the temperature increases by 0.14 Kelvin. So what does it translate to over here? That is, we have got a loss of 250 watts. Okay, we have got a loss of 250 watt. They have told that the R theta, right? We call this as R theta. That is the thermal resistance. Thermal resistance. Okay, it is expressed in Kelvin per watt or in degrees Celsius per watt. Both are same only. So it means that for 1 watt of loss that occurs, the temperature increases by 0.14 degrees. Okay. So this is your RT. Right? So, so in that case, we have got a total loss of 250 watts. They have mentioned R theta is 0.14 degree per watt. So what will be the temperature rise in the device? What will be the temperature rise? It will be directly 250 into 0.14. All right. Into 0.14. Right. And this is around 35 degrees. Now we may think that, okay, let's say we were operating at an ambient temperature of 30 degrees. The temperature rises by around 35 degrees and this becomes 65 degrees. So why should I even attach a heat sink, right? Like I need not attach a heat sink, I can directly run it. Okay, right? Is this fine? Like, do you agree? Why should I attach a heat sink? Like I can directly run it, right? Like, is this argument correct? Do you agree with this? Why should I attach a heatsink? But you note that, see,
because it,
uh,
it could be because the environment it will be there.
right.
Environmental effect will be there. Yeah,
Right.
this 30 you are added as ambient, correct, no sir?
Correct. So
Yeah,
now you
but
understand that
ambient condition
what are
always will not be the same.
ambient temperature will always not be the same. Okay, so let's say that there is plus or minus, let's say there is plus or minus even 50 degrees, right? Worst case. Let's say the ambient is 80 degrees. Even if it is 80 plus 35, it will not exceed beyond 175 degrees. 175 is too much. So why should I attach a heating is the question, right? Why should I do some heating calculation and all?
Your voice is
The
not
answer,
clear.
okay. Okay, so now is it better? Now is my voice clear?
No.
Sir, your voice not clear. Hello.
Yeah. Okay. So actually my earphone is not getting connected. I don't know why. So that's why I'm keeping it as computer audio. So probably that's why it's not coming. So I'll just log out once and log in once. Okay. Yeah. So now is my voice a little better, or is it the same?
Correct, sir. It's okay.
Okay. Yeah. So as I was telling, you can directly add this temperature part only if your kind of a surface area is big. Okay. In our case, you know that the devices or the dies are going to be very, very small. The die size will be something like, let's say 3 mm cross 5 mm. This will be the die size. So you note that the entire power loss, right? The entire power loss is going to occur in a very, very, very small area. This is your junction. As in like this is your junction. Okay. This is going to occur in a very small area. Okay. As far as heat is concerned, right? If you have a larger area for dissipation, the better will be the cooling. So what's going to happen is within a very small area, there is going to be a huge power loss, right? And because of that, what would happen is within a small area, there is a large heat flux. We call this as heat flux. Okay, the heat flux will be very, very high if you don't have a heat sink attachment. That is why what we do is we have a thermally conductive surface attached to this small area, which will kind of spread out the heat. Do you understand? There should be a thermally conductive surface which will spread out the heat. Okay, so that my temperature rise is limited, right? You cannot directly do this addition. The reason being that this entire loss occurs in a very, very small area. Okay, that is the die, and you don't want something like that to happen. Hmm. Okay, fine. So what people do is they attach heat sink, right? And generally people can attach one heat sink per device, or they will attach one entire heat sink for two devices or multiple devices. Okay, so let's say you take a half bridge. Okay, so you take a half bridge like this. Okay, this is your buck converter only, right? So people will attach one heat sink for this device also and this device also. Okay, there will be one heat sink for both devices, and in most of the cases you will see that the heat sink is not only thermally conductive, it is also electrically conductive. Okay, so the heat sink is not only thermally conductive, it is also electrically conductive. So in that case, can you directly attach the heat sink onto the devices, or should there be some medium?
So how can we connect electrically connect the heat sink
Correct.
for the
So
both
if you
switches?
directly connect, yeah, so it means that you are shorting both the devices, right? So you cannot directly connect the heat sink between with the two devices directly, because it's essentially shorting the devices. Okay, so there will be the die first. Okay, so there will be a die, and after this what they will have is they will have an insulating layer. There will be a very small insulating layer. Okay, so we call this as the interface material or thermal interface material. This will be electrically isolating. Okay, so this is your die, and this is your TIM material or thermal interface material. Again, there is another die or your other device, and then there will be one insulating material, thermal interface material. We call it a TIM layer. Okay, and then after this, you will be having your um, common heat sink. This is your heat sink. Can you visualize? This is the side view. Okay, two devices are there, and then there will be the thermal interface material, and then there will be heat sink. Can you visualize this? Is this fine?
Yes, sir.
Okay, this is how your attachment looks like. Fine. Okay. Okay, so we will worry about this later, but right now for our computation, let's assume that there is only one device and there is only one heat sink. Okay. Okay. So you understand that when we tell analogous to, let's say you have three resistors, right? You connect three resistors in series, right? We tell that the same current flows through each of these three resistors. Now you imagine in terms of heat, okay? Heat is getting generated over here in the die. The heat has to flow from the junction through the device through the TIM material to the heat sink. Okay, so you understand that the heat flux is same, right? The heat flux is kind of same. It will flow through the die, it will flow through the TIM material, and then it will flow to the heat sink. Do you understand? It's analogous to three resistors connected in series. It is like three different materials are just connected directly, and the heat flux finds a direct path. Okay, is this fine? Okay, and just like see, so let's say that excuse me. Okay, so let's say that you had 40 volts over here. Okay, or for ease of computation, let's say we have 30 volts. There's a current that's flowing. There will be a 10 volt drop over here, 10 volt drop over here, 10 volt drop over here, and this will be your ground. Okay, so this is your source, 30 volts, and there is voltage drop everywhere, something like this, and then you reach the ground. Analogous to that, you will have your heat source over here. Let me call this as the junction temperature. Okay, then a heat flux is flowing through a thermal resistance. Heat flux is flowing through a thermal resistance. So there will be some drop. There will be again some drop, and this will be your final ambient for your surroundings. You understand? So this is your heat sink. This is your TIM material, and this is your device. You understand this? The entire power loss is happening in the junction, so there will be a junction temperature increase in the junction. Then that heat flux is flowing through the die. That is the first stage, and then some heat. Then the same heat flux flows through the TIM material. That is the second stage, and then there will be some heat flux through the heat sink, right? Then it finally gets connected to the ambient. Okay, so if we have to draw the electrical equivalent, all right, so let's say this is your V. This is how we draw in electrical terms, right? There's your R1, R2, and R3. Analogously, you can draw for heat also. Okay. So you note that there is a potential Tj. Okay. And because of that, there will be a heat flux phi. Okay. It flows through so this is your junction side. Okay, it flows through the device. Okay, r theta device, right? Or I will call this as oh, okay, it got erased off. This is your Tj. And this is your ambient. Okay, so there is a heat flux phi. It flows through your r theta device, right? So r theta device. Now it was initially in the junction. The heat flux flows from the junction to the casing of the device. Okay, case of the device. Then it flows through the TIM material. Now from the case, it has reached to the heat sink body. Okay. Then it flows through the heat sink, R theta heat sink, and now it has reached the surroundings. Do you agree with this? Is this fine? Do you agree? Okay. Now we will just write a KVL equation. Okay. So what will be the KVL equation? Potential difference is equal to I into R. So Tj minus Ta, right? Potential over here, potential over here. Tj minus T ambient, right? Tj minus T ambient will be equal to some current into R theta device plus R theta tim plus R theta heat sink. Okay. All right. Okay. So now you tell me what is this flux actually? So what causes temperature increase? Huh? Yeah. So what?
The ambient will not
Yeah.
be ambient.
No, it will be ambient. Na? So what is Ohm's law? Ohm's law is V tell V equal to IR. Basically, it's respect to ground, right? So it is actually delta V is equal to I into R, right? Whatever is the potential difference, that is I into R. Similarly, over here, what is the temperature difference? There is a temperature rise happening in the junction, and we assume that the ambient is, let's say, a fixed temperature, right? Let's say 35 degrees or something, or 30 degrees. So what is the junction temperature increase compared to the ambient? That is what we want to compute. Okay. See, directly analogous to Ohm's law, V equal to IR. So voltage is similar to your temperature difference, delta T. Okay. R is proportional to your thermal resistance, R theta, thermal resistance. My question is over here, the current is what is causing the drop, or current is causing your temperature, current is causing your voltage difference. Over here, what is causing your voltage difference? Can you tell me what is this I? So in terms of why is this heat increasing? What is the primary factor that contributed to the heat? Can you tell? What is the primary? Why is the, let's say I have a device, I'm not operating it at all. Will there be any heat loss? No, right? So why this heat loss is happening? So why this heat loss is happening? What is causing this heat? Conduction takes place, correct. So when conduction takes place, there is some laws, right? We computed what is the laws. We computed what is the conduction laws. We computed what is the switching laws. So this loss is the factor that is making the temperature rise to happen, right? We saw what is IRMS and all. Eventually that IRMS square into R plus whatever is the on-state drop loss, right? That is what is contributing to the heat increase. So this over here, right? This is actually your P that is happening to the in the device, right? This is the power loss. The power loss is actually causing your delta T increase. Do you agree? Physically, you think. Don't think that, okay, why did he replace current with power? No, no, it's not like that. It's like you think physically, analogous to Ohm's law. What is causing your temperature increase, right? Over here, what caused your delta V? It was because a current was flowing, right? If your current is zero, then your voltage is also zero. Voltage difference is also zero. Similarly, over here, if there is no power loss, then there is nothing, right? If there is power loss, only because of power loss, there is temperature increase and all. Do you agree with this? Is this fine? Both of you?
Yes, sir.
Okay. So just remember Ohm's law. It's like
Yes, sir.
this is analogous to V, this is analogous to I, and this is same as R. So delta T is basically P into R theta, something like this. So in our thermal chain, we call this as thermal chain. Okay. So you started from junction, R theta device. We call R theta device in short form as junction to case. Okay. R theta junction to case. We are from junction, and the heat flux flows through the outer body of the device or the casing of the device. So R theta JC or R theta junction to case. Okay. Now the point is this particular R theta device is given in the data sheet. Okay. This is what is given as 0.14 degree per watt. Okay. This is given in the data sheet. Right? R theta junction to case is given in the data sheet. Right? So this is given. This is given in the data sheet as 0.14 degree per watt. Hmm. 0.14 degree per watt. Kelvin per watt or degree per watt both are same because why? Kelvin is basically 273 plus degrees, right? So if you differentiate it, it's going to be differentiation of constant is 0. So it's same only. So degree per watt or Kelvin per watt is same. Okay, fine. Purida, is this fine? Is this fine? Both
So
of you, is this
you're
fine?
saying that
Oh, my screen is not visible.
yes, it is visible.
Uh-huh.
You said that the data given in the data sheet, that is
Oh, that was
R
this
theta
one.
device junction to case, case of the device, you said, right?
Yes, R theta
But
JC.
but
Hmm.
in that we have derived here, it is R theta device plus R theta thin layer plus R theta heat sink.
Correct,
So
correct. So now the
these all
point
creates.
is, uh-huh, these are all, uh-huh. So now I will tell you. So now the point is, now you will know, right? Like let's say your converter is operating in an electric vehicle. Okay, so your ambient temperature is, let's say, we always compute for the worst case. Okay, let's say that your ambient temperature is somewhere around 50 degrees. Okay, let's say that your ambient temperature is 50. Okay, so the ambient is 50 degrees. Okay, and you computed your power loss, right? We computed the device loss was how much? 250 watt. Okay, device loss is 250 watt. And you know what is the device from the data sheet? You know that R theta JC is 0.14 degree per watt. Okay, they have given that the device can operate till a maximum of, right, the maximum temperature that the device can operate is 150 or 175 degrees, something like that, right? They have given this is the junction temperature, maximum it can operate. So if this is the maximum, as a designer, what you will do is, I don't want to go anywhere above 100. Okay, 100 is too much, right? Boiling point. So I don't want to go anywhere about this. So what I will have a constraint is that I will have a constraint that my maximum junction temperature can be only 100 degrees. Let's say, okay, maximum temperature can only reach 100 degrees. Okay, so I know what is TJ, I know what is T ambient, right? I know what is the power loss, and I know what is the R theta JC. I have to choose a proper value of TIM material and proper heat sink material so that my temperature gets constrained to 100 degrees. Do you understand this? What I'm trying to tell? as a designer, I
We
have
have
to
to
choose my thin material. I have to choose my heat sink so that my delta T is less than or equal to 50 degrees under the worst case operating condition. Okay. So if you're operating in electric vehicle, there will be acceleration, there will be steady state operation, there will be your you will operate at 20 kilometers per hour, you will operate at 100 kilometers per hour. So for the worst case, right, at 100 kilometers per hour, where you will have maximum torque and maximum current will be drawn, right? That is where your converter is operating at the worst case. At that point, you don't want to blow up, right? So you will compute for that particular operating condition, you will compute what is your loss, right? You will compute what is P, and you will compute what is P, and then you will calculate what should be my heat sink value, mainly this. What should be my heat sink so that my temperature is less than 50 degrees. Temperature rise is less than 50 degrees. Do you understand this? This is the design problem.
Yes.
Okay. Right. So now let's take an example and then calculate, okay? Is Purida, like, is this fine to both of you?
Yes, sir.
Great. So we will take another problem,
This,
okay? We will take
here one doubt, because now delta
Hmm.
we from the power and from the data sheet point, we calculated the uh, uh, temperature delta. Correct, no, sir?
Correct.
Delta is around 35 degrees. Means ambient to junction temperature.
Correct. Ambient to junction temperature, yes.
Am I right?
Hmm.
The delta T is, as per
Hmm.
data sheet and power calculation, it is 35 degrees. So
Right.
we have to calculate heat sink to transfer these 35 degrees, because junction temperature to this ambient to reach. So the heat sink to be decided to transfer this amount of heat.
Right.
No?
Correct. But now what would happen is that because you are adding additional stages, right? What would happen is this also has some R theta, right?
Yes.
The idea of adding a heat sink is, as you told, like we have to transfer the heat. That is
Yes.
one. Second is you want to spread out the area and all. But that also has some R theta. So that also has to be taken into effect. That is what we are doing. Heat sink. So ideally, you want an infinite thermal conductivity for any material, right? But that is not there. Every material has a particular value of thermal conductivity. Based on that, there will be some R theta, right? R theta is what? Degree per watt. It is like ohms only. R is what? Rho L by A, right? Similar
Yes.
to that, you can write for this also, you can write L by K into A, where K is your thermal conductivity. That is your R theta. Very analogous, right? Very simple. Rho is the resistivity. Over here, conductivity. So it's coming in the denominator. Okay. L by K
No,
into A, where K is.
my clarification. This okay, sir. My clarification was only that delta. So 35 degree. So 35 degree to pass or spread out or transfer the place from
Yes,
junction
yes,
to
yes,
this.
yes, yes,
That
yes.
is the minimum level. Minimum level. Correct.
Correct. Okay. Okay. So I have one numerical problem just to compute what is the what is this heat sink thing, right? So we will see this particular problem and close off. Okay. So the question is this. Right. So the question is this. Consider a MOSFET whose thermal resistance, right, R theta JC is 1.8 Kelvin per watt. Sorry. And K is to heat sink thermal resistance. K is to heat sink thermal resistance is 0.5 Kelvin per watt. If the device is mounted on a heat sink that has an R theta of 7 Kelvin per watt, then what is the maximum power that can be allowed to be dissipated? The MOSFET given max maximum junction temperature of 150 degrees and ambient temperature of 40 degrees. Hello. Yeah, so this is the question. Okay. See, there is a MOSFET. Its R theta is given. R theta junction to case, right? And case to heat sink thermal resistance is 0.5 Kelvin per watt. So case to heat sink na, case to heat sink means which watt? Which stage? Case to heat sink means it is the thermal interface material. Case to heat sink means it's the thermal material, right? Okay, so TIM material R theta is 0.5 Kelvin per watt. If the device is mounted on a heat sink that has an R theta of 7 Kelvin per watt, then what is the maximum power that can be allowed to be dissipated in the MOSFET? This is kind of the reverse question. They have given you all R theta, right? And they have given that the maximum junction temperature is 150 degree, ambient temperature is 40 degree, right? So they have asked you how much power maximum you can dissipate, okay, so that your maximum junction temperature should not be breached, right? This is simple, right? Directly we can answer, right?
Yes, sir.
So
Del T
R
is
base
del T equal to P into R.
del V is correct. So del T is equal to P into R, right? So R tim is 0.5 Kelvin per watt. Our heat sink is 7 Kelvin per watt, okay? And they have told that Tj is 150 degree, Ta is 40 degree. See, this is in Kelvin per watt. Okay, Kelvin per watt and degree per watt, both of them are same. Do not waste your time converting this degree to Kelvin and all. See, if you convert this to Kelvin, right, this will be 273 plus 150 Kelvin. This will again be 273 plus 40 Kelvin, right? So eventually it is Tj minus Ta. Tj minus Ta means again the 273 will cancel. Okay, I have seen people who unnecessarily convert this degree to Kelvin and all. They have given in Kelvin per watt just to confuse you. Okay, do not add this 273 and all, right? Because basically you are taking delta T, not absolute temperature. It is Tj minus Ta. So 273 and 273 will cancel out if you subtract, correct? Right? So unnecessarily don't convert this Kelvin to degree and all. If it is in Fahrenheit, then it's a different issue. That 5/9 thing will come, but or else you need not worry about it. Okay, so over here we know that delta T is basically P into R theta. So Tj minus Tm is equal to P into RJC plus R Tim plus R heat sink, right? So what should be P? Tj minus Ta is 150 minus 40, which is 110 divided by 1.8 plus 0.5 plus 7. How much do you get? I think you will get 11.8 watts. Are you getting this? Is this fine? Like, are you understanding this?
Yes, yes.
Okay. Selvakumar sir, is this fine? Direct calculation only, right?
Actually, I'm not getting it. So my answer different.
Acha, I did some calculation mistake. 1 minute. $150 minus 40 is 110. Okay. 110 divided by
Yes, yes, correct. Correct.
11.83, right? I think that's what I'm also getting. 11.83 I'm getting. Yeah, 11.83 watts. Okay. So now the next question is, the converter, the next follow-up question, okay, B in the same question. The converter switching frequency is increased. Okay. So if the switching frequency is increased, what will happen to the losses? Will they increase or decrease?
Decrease.
So what will happen if the converter switching frequency increases?
Losses will decrease.
Turn on and turn off.
Turn on and turn off time? What's it?
It will be fast.
And
Turn on will be
turn
fast.
on time
So
will-
switching loss will be reduced.
Okay. So now the
Switching
question
loss
is,
will be reduced.
let's say that your T on and T off, right? Let's say that they are 20 nanoseconds. Let's say, okay, let's say 20 and 30 nanoseconds. Okay. Initially, I was operating at 50 kilohertz. Now I am making it 100 kilohertz. Okay. The T on and T off are same. I am keeping both T on and T off as same. So then what will happen to the losses?
No, if
What?
turn on, turn off, if you keep same, it will be, it will not no change. It will be loss will be same.
Loss will be same.
No,
So
on time, if on time, if there is no change.
on time and off time are same. Okay. So what will happen to the power loss? Will it be same or will it increase or decrease? Right. So if we go to the last class, right, we concluded at the last point. Huh. we computed what is the power loss, right? We computed what is the energy loss under this curve. So energy, we computed this is some microjoules, and after that, what is power loss? Power loss is basically E by T,
Power
energy by time, or
into switching
energy into
frequency.
frequencies. Wait. So a power is energy into frequency, switching frequency, right? So
Yes.
if your switching
Yes.
frequency increases, we saw that, see, at 10 kilohertz, for same energy loss at 10 kilohertz, the power loss is 1.5 watt. At 100 kilohertz, the power loss becomes what? Directly, it's multiplication, right? Energy into switching frequency. Hmm. Do you remember this, Selva Kumar sir? In the last
Yeah,
class, we
yeah,
saw.
yes, yes. Yeah, yeah, yes, yes.
So, switching loss increases if your switching frequency increases. Okay. So, this is the major drawback. Or else, why should we even operate at 10 kilohertz, 100 kilohertz? We can directly go to 10 megahertz or 100 megahertz, right? Why are we not going? Reason is because of this. Okay. Switching losses will increase directly if your switching frequency increases. Okay, so this is the drawback. So one basic thing, right? If your switching frequency increases, the size of your inductor and capacitor will decrease, right? Even in buck converter, you would have seen the computation of how do you calculate the value of L and C. You will see that it's inversely proportional to frequency. If frequency increases, your L and C value decreases. But on the other hand, if your frequency increases, the switching losses to the device will increase. Okay, please don't forget this, right? For the same energy, of course, for the same switching energy, which means that for the same turn on and turn off time and all, same timings, your energy, if your energy is same, if you just make it a function of switching frequency, as the switching frequency increases, directly you can tell that switching loss increases. Do you understand, both of you?
Yes, sir, yes, sir. Actually, if morning itself, morning also I seen same if I tried for that.
No worries, no worries.
Yes.
Okay. So the next question is that the converter switching frequency is increased. Okay. And so the loss increased to loss increased to 15 watts. In the previous problem, we calculated the power loss is 11.8 watt, right? Power loss was 11.8. This power loss includes both the switching loss and then the conduction loss, both of them, right? But over now, what happened? Some component of the switching loss has increased because the switching frequency increased, switching loss also increased. Okay, the conduction loss may remain same, but switching loss has increased. Because of that, your total power loss has increased from 11.8 to 15 watts. Okay. Now the question is, what will be the junction temperature? What is the junction temperature now? Okay. In the previous problem, everything else was given, right? TJ was given, TA was given, RJC, RTIM, R heatsink was given. Okay. What is the power loss? Now they have given the power loss. They have asked what is the new value of TJ. Earlier I was operating at 150 degrees with 11.8 watt loss. Now I have increased the loss from 11.8 to 15 watt. What is the new value of TJ is the question. Are you understanding the question? So again, Tj minus Ta is P into R theta Jc plus R theta Tim plus R theta heat sink, right? So they have asked what is Tj. So Tj, Ta is 40. Power losses they have told 15 watts, right? And everything else is same, 1.8 plus 0.5 plus 7. Both of you, are you understanding what is happening over here? Like, is this fine?
Okay. This power loss is only increased to 11.83 to 15 watt. It's not in
Yes.
addition to 11.83.
No. Power loss is increased to 15 watts. It is not increased by 15 watt.
Okay. I understood mistakenly. Okay.
No worries. Okay. Okay. So now we have increased the power loss to 15 watt. Now with this new power loss, what is the junction temperature? I am getting 179.5 degrees. Is this fine? It's a straightforward question only again. Power loss is given, everything else is given. What is the junction temperature? Is this fine, Anandi and Selvakumar sir?
Yes, sir. It's fine.
Anandi, is it fine? Excuse me, Anandi. Is this fine?
Sorry, sir. I forgot to.
Okay, fine.
Sir, if we increase the switching frequency, there will be an increase in power loss.
Yes. So actually in the last class we derived it, okay, but so what happens is, do you remember we were seeing the mechanisms, right? How it turns on and turns off and all.
Yes, sir. Yes.
So in the last class, we kind of derived what will be the period, okay? What will be the turn on delay time, what will be the rise time, and what will be the current rise time, and what will be the current rise time and what will be the voltage fall time. This and this. We derived both of these expressions. Okay. Once you derive what is this, you understand that every time the device turns on and turns off, you will see something like this, right? First, the current increases. This you see this green waveform, current increases during the current rise time. And after the current has increased, we saw that the diode was conducting, antipole diode was conducting. So after the current has reached the full steady state value, the voltage will fall, right? VDS has fallen, right? So what is your power? Instantaneous power. P is V into I, instantaneously, V of t into I of t. So if you assume that the current rise is linear, voltage fall is linear, the power loss will be something like this dark blue one. You understand now?
Yes.
Something like this, right? So something like this will happen every time the device turns on and every time the device turns off. All right.
Okay.
So what you want is to actually to decrease this TR and TF as much as possible so that this power loss happens for a very small period, but still it will happen every time, right? Because your voltage is, let's say, very high voltage, 400 volts or something like that, current will also be high. So if you have to calculate what is the average power, this is just the instantaneous power, right? If you have to calculate what is the average power, what will you do? First, you will calculate the area under this, right? Area under this will give what? Area under power curve will give energy, right? Power into time is energy, right? So you will calculate the area. The area is it's just a triangle, right? Two triangles together, half B into H. That is what we have done. So half into B into H. Okay. So this will give the area. That is your energy. To come back to the original power, right? So this kind of power loss happens every time the device is turning on, every time the device turns off. So when will the device turn on? The device will turn on once in every switching cycle. Okay, that is why we compute the average power is energy into frequency, energy into switching frequency. Why? This energy loss happens every time the device turns on, every time the device turns off. The device will turn on and turn off once in every switching cycle. That is why average power is energy into switching frequency. Do you understand? So that is why as frequency increases, the power also increases. Switching loss increases, to be exact.
Okay.
Okay.
Yes, sir.
You can go through the slides if you want. I will upload.
Okay, sir.
Oh. So as I was telling, in the second part, the switching frequency increase, the loss increase. The new junction temperature is 179.5. Okay. But see the first part of the question, they have told that maximum junction temperature is 150 degrees, right? If you operate like this at 15 watt, then the temperature is exceeding beyond 150 degrees, right? The temperature is going to 179.5, device will blow. Okay. So now I have to modify my heatsink design properly, right? I have to modify my heatsink design properly so that my junction temperature goes back to 150 degrees. Purida, like, do you understand?
Yes,
I
sir.
have to, I will operate at 15 watt loss. I have to find out what should be my R theta heat sink so that my junction temperature goes back to 150 degrees. That is your C part. Last part is determine the thermal resistance of a new heat sink. That will limit the junction temperature to 150 degrees. Purida, the question, the flow, are you understanding? Initially, we calculated a power loss. Then we saw that, okay, the switching frequency has to increase. So the power loss increases. But if now the power loss increases, the junction temperature is going beyond 150 degrees, right? This is beyond 150 degrees. So now I have to do my design properly so that I will choose a new heat sink, right? So that my junction temperature is restricted to 150 degrees with 15 watt power loss. Do you understand?
Yes, sir.
So again, we will use the same thing only. So Tj minus Ta is equal to P into R theta Jc plus R theta Tim plus R theta heat sink. Now Tj should be restricted to 150 and the power is 15 watt. R theta Jc is fixed at 0.8, R theta Tim is 0.5. They are asking what should be the R theta heat sink? What should be the thermal resistance of the heat sink so that I am able to dissipate 15 watt of power and maintain the junction temperature at 150. Okay. So if you calculate it, R theta heat sink will be how much on 110 divided by 15 minus 1.8 minus 0.5. I'm getting 5.033 degree per watt or Kelvin per watt. Is this fine? So initially the R theta of the heatsink they gave in the problem was 7 Kelvin per watt, 7 degree per watt. But with that heatsink, we are seeing that it is not able to dissipate the heat properly. So we need a new heatsink with a lower R theta, right? Lower R theta means better thermal conductivity. Okay. Or yeah, better thermal conductivity. So the heatsink design will be a little different, right? It may be a bigger heatsink because rho L by A, right? So it might be a bigger heatsink. Do you understand this
Yes, sir.
problem? It's very simple, very analogous to V equal to IR, right? Just you need to design properly. So if let's say they have given that your R theta heatsink is 3 degree per watt. If it is 3 degree per watt, then the junction temperature will be even lesser. Okay. Selvakumar sir, like, is this fine so far? Today we have seen problem on loss calculation for the
Sir,
device
yeah,
conductor loss. Huh? Yeah. So we have seen a
Here,
problem of loss calculation, that is conduction loss calculation for IGBT, and we also saw a problem on heat sink calculation. Okay, we saw in first principles how this heat sink is computed. This we derived the thermal chain. Okay, and then
here one doubt, sir. Actually,
I
that
will.
the delta, the junction temperature,
Mhm.
uh, actually because of 179 is that we are finding the R theta, no? From 179 to we have to bring down to 150. So
Yes.
then the TJ it should be 179. No?
No, no, no. See. We found out that the point is with the same heat sink, right? Initially you understand the problem. Initially you were operating with 7 degree per watt heat sink. Okay, they told that junction temperature was 150 degree. They found out the loss. Then what we
Okay.
did, we increased the switching frequency to a higher value. So what happens is if you directly increase the switching frequency, your loss also increases. Your loss increases. So now the device was operating at 150 degree. Now it starts, the temperature will rise to 179 point something, 180 degrees somewhat. Okay. If you just directly increase the switching frequency, you cannot operate your converter directly, right? Because if you directly operate your increase your switching frequency, your device temperature is increasing, it will blow up. Okay, right? So now the point is, okay, if I have to continue operating at uh, this higher switching frequency with a higher loss, then I have to change my heatsink design, right? I cannot operate my device at 180 degrees with higher switching frequency, right? So I have to, what I should do is if I have to operate
Okay.
the device at higher switching frequency, I have to change my heatsink completely. Okay. That is why we computed what should be the heatsink so that my device can now operate at this new operating condition. And mind you, this is not dynamic. Okay, like it's not like okay, directly the converter is operating at let's say 10 kilohertz. I will directly increase the switching frequency from 10 kilohertz to 30 kilohertz. No. Okay, you cannot directly do that. They have in the problem as a design problem. They have asked initially you designed it for one switching frequency. Now they are modifying the design a little and they are telling that now you design it for 50 kilohertz or something like that at a higher switching frequency. So now that you have modified the design, your heatsink should also be changed. That is the point. Okay. And practically in the data sheet, they will give 150 degrees as maximum limit and all. You will never go near that value. Practically, when you calculate, you will keep maximum limit as 100 degrees or maximum 110 degrees, something like that. You will not go near 150s and all, 150 and all. Okay, 150 is the maximum temperature. As a designer, you should keep it at 100, 110 like that. Do you understand?
Okay.
Okay. So Anandi, is this fine?
Yes, sir.
Okay. Mostly these are, you would have seen in the lecture slides also. Like you have three kinds of heat sinks. One is naturally cooled heat sink. One is fan cooled or fan cooled or forced air cooled. The other one is liquid cooled or water cooled. So if you give forced air cooling, right, then the R theta will reduce more because now you are having a fan which will take away the heat, right? So the R theta will be somewhere around 1 degree per watt or even lesser, 0.5 degree per watt with fan cooling. And with water cooling, which people go for, like if you're going for very high kilowatt, right, very high power, then in that case, you will see that there is a large heat dissipation. Okay. Your heat sink requirement will be something like 0.1 degree per watt or even lesser. So to achieve that, people go for water cooling. They will circulate water. You imagine something like what happens in your refrigerator, right? You would have studied the operation of refrigerator. It basically takes away the heat by circulating a coolant, right? Same principle will be used over here also. Okay. So, is this fine? Both of you, please go through it. Okay. This is what I wanted to
Okay.
discuss regarding heat sink calculation. So, yeah. So we will close for the day today. Okay. Yeah. So thanks for
Okay,
attending
sir.
both of you, and yeah, next week we will probably go to a different
Thank
topic.
you, sir.
Okay. Yeah.
Good
Bye bye.
Thank you, sir.
Yeah.
Good night.
Good night.